Hello and welcome to Power Grid Expert, the YouTube channel about electrical distribution grids. Today's video is an introduction to the general structure of a power supply grid. If you like this video, please remember to press the follow button. If you have questions at the end of the video, please do not hesitate to contact me. My contact data is in the text below the video. Today's topic is the general structure of electrical power grids. I do this with the example of the structure here in Germany, although you can assume and you can keep in mind that the structures worldwide do not differ that much in this field. But of course, I have to put on some drawings, and I do this according to Germany. The structures in Germany. So the three topics for today is structure of the energy supply grid, the distribution grid, which is especially my focus, and the last point, current and future challenges, also here with a focus of the distribution grid. We start with this general structure. This is unfortunately a drawing in German, but there are lots of pictures in it, so I think it's easy understandable. We start at the generation point of the energy. This is typically the power plants. We have, for example, coal plants, we have water plants, atomic plants, of course, small industrial plants as well, waste plants, and so on and so on. In the classic structure of the energy supply grid, these are quite big power plants which are scattered over the country. And the energy that is generated there has to be transported to the areas where the energy is needed, to big cities, to industrial zones whatsoever. In general, we can say every transport of energy via cables, via overhead lines has losses. And of course, we want to reduce the losses. And the higher the voltage, normally the less the losses. So easily we can see that if we want to bridge a big distance between generation and the customer, we go up to high voltage or very high voltage, 110 kV, 220 kV, 380 kV, or even higher, or even to DC connections. Via these transport lines, we reach generally the region where we want to distribute the energy. So we transform the voltage down from 220, from 110 to so-called medium voltage level, which is typically between 10 kV, 20 kV, 36 kV. Officially, medium voltage starts at 1 kV and goes up to 53 kV. Once we are in the region, we go via a transformer station, via a substation, transformer station in this case, from the high voltage to the medium voltage, for example, from 110 to 20 kV. And in this transformer station, we have the feeders going out to the city, to the industrial zone. And at the feeder, we have the so-called substations. The substations are small transformer stations with a transformer transforming the voltage from a medium voltage level down to low voltage. If we talk about low voltage, it's still 230 or 400 volts for you, which you might consider still as high voltage, but electrotechnical spoken, this is low voltage. With a low voltage, there is the last part of the distribution. It takes place in the low voltage cables going to to the houses, going to smaller industrial companies, for example. And then we have the customer and the endpoint of our energy supply grid. So coming from a generation, going to the customer, first we go high in voltage to bridge a long distance. Then we go down, we step down in the voltage from high voltage or very high voltage to medium voltage, from medium voltage to low voltage, and then we reach the customer. In all these voltage levels, we have connections to power plants, we have connections to customers. Big industrial customers sometimes connect to very high voltage or high voltage lines. They have such a high demand that it's better to connect here. We also have the DERs, the decentralized energy resources, wind farms, solar plants, for example. They are distributing, they are feeding the grid on different voltage levels, sometimes on low voltage levels, most often on medium voltage levels. But if you look at the offshore parks, of course, they have their own high voltage connection. The most important players, and also here the most important players in the market, I am doing here the example according the regulations in Europe, with examples given in from Germany. But basically this concept you can find all over Europe, and for some countries also outside of Europe. We have coming from if you just go one step back to the graphics, coming from the high voltage level, we have the operator that runs this high voltage and very high voltage networks. These are the so-called transport grid operators. There's one example of one here in Germany. Then one level down, we have the distribution grid operator, which is the company that runs and operates the grids in the medium voltage level, sometimes also in the high voltage, but the main focus is the medium voltage and the low voltage. We have the metering point operator. This is something given by European regulations. As far as I know, in most cases, this is done by the distribution grid operator, but generally this can be another company as well. Of course, we have the power plant operators. We have the power supply companies, which is basically the company you have your private contract to buy energy from. We have some mixed forms, and in most countries we have a regulatory authority. In Germany, it's the Bundesnetzagentur that keeps an eye on the whole market. It's not a fully open market, it's a regulated market. So there are rules, there are restrictions, there are regulations, and they are specified by these authorities, and the market players have to follow them. What we can see here is there's lots of different companies. As a private person, you might only have contact to your distribution grid operator and to your power supply company, and nobody else. And in former times, if you look back like 20-30 years here in Germany and in Europe, this was all one big company having the monopole over the generation, the transport, the distribution, and the end customers. And therefore, this has been split up in different companies to simulate somehow an open market, which if you have a detailed look, it's not, but at least to have some competition between different distribution grid operators, um, different power supply companies, and so on. So we will have a look at the distribution grid. As I mentioned, this is especially my expertise. So the last 18 years, I've been working in the distribution grid, and especially here in the so-called secondary technology, which is everything that is not primary technology. So everything that is built in to measure, to control, to detect faults, protection relays, to communicate, RTUs, for example, and stuff like that. The distribution grid is marked here with a green background. So normally we start to call it distribution grid from the power transformer coming from high voltage to medium voltage. And already that transformer station here is part of the distribution grid, as are the following substations coming here, as also DERs who are supplying to the medium voltage level, to the low voltage level, of course, as well. And this comprises also cable networks, overhead lines, and the endpoint of the distribution grid is the connecting point to the end customer. Let's have a look at the general structure at medium voltage level. So if we go one step back, we are actually now looking at that point here at the power transformer from high voltage to medium voltage, and this bus bar here and the feeders going out here to different regions, to different customers. And this is shown here in a more technical drawing. So we have transformers. Sometimes we have redundancies. So in this case, we have two transformers. So if one transformer has a problem, we can switch over easily to the reserve transformer, or both are running in parallel. We have a bus bar within the transformer station, and we have so-called feeders. The feeders are the connecting point to, let's say, to the outside world, which means there is a cable, there's an overhead line, and on that overhead line or cable network, we have so-called substations. So remember, we are here in medium voltage level, 20 kV, 10 kV. So we still need somewhere a transformer to step down to our household voltage, 230 or 400 volts. In some countries, 110 volts. So these substations are symbolized by these small black stripes here. They're like on a daisy chain. They're like on a pearl necklace, with one difference, that at some point this line is open. This is symbolized here with the red cross, the red mark. Why I will explain in later videos. This is mainly for easier fault detection. We keep these lines normally open, but not always. So why is the structure of this network like a chain, like a necklace, and not like just a radial network? That is explained in a few minutes. So if you look here, how does a typical substation look? You can see here let's say the recent modern version. Inside there's a transformer from medium voltage to low voltage. There's a medium voltage switchgear. There's a low voltage compartment with the low voltage cables going out. There is also some older versions. Sometimes you still see them. Basically, same technology or the same task is done here as it's done here. The older the substation, the more space has been needed because recent SF6 switchgears or the future non-SF6 switchgears, they need very little space in comparison to air-insulated switchgears. So the older stations are normally much bigger. Also, in some countries, we do not have these substations at all. We have just the transformer. If typically in overhead networks, then the transformer is just mounted at the pole of the overhead line and with some switches and fuses there without a separate housing. So coming back to why do we need these two parallel lines, and we have this connection point. This is quite easy when we have a look at what happens during a fault. So I'm giving here water examples instead of electricity because it's always easy to understand here. So we have somewhere the water reservoir, we have so let's say the generation of the water, and we have the consumer here. In this case, it's a small mill, and this mill is supplied by this water reservoir. If as long as it's full and the water is running, the mill can produce the flour whatsoever. So what happens if there is a planned or unplanned accident with that pipe, with that water pipe? The supply is stopped, the mill stops, of course, and there is no supply anymore. And then this mill has to wait until this pipe is completely repaired, which can take several hours up to several days, depending on the severity of that interruption. Of course, this is not what we want in our energy supply, in our electricity supply. We want to prevent that people are out of power for several hours or even several days. And the higher the voltage level, the more people are affected by an outage. So what we do here is we make parallel lines, and these parallel, well, in this case water pipe, if there's a problem in one pipe, there is still the supply over the other pipe. So let's have a look inside the substation. What's inside? I already said there is a switchgear, there's a transformer, and to give you an example from the low voltage, what's basically in there is two switches and an AC adapter. The switch is the medium voltage switch, and the AC adapter is in the transformer. Everything looks a bit bigger, but basically the task is exactly the same. The only difference, these devices here are made for 230 volts. This adapter gives out, for example, 5 volts or 10 volts. And here we talk about 10,000, 20,000 volts medium voltage level. And also the transformer transforms the 10,000 to 230 volts or three-phase 400 volt. So the only difference here is really the voltage level and of course the power level. But basically these tasks are pretty much the same. Let's have at our last point a little look at current and future challenges for the networks. Also, this is with these challenges are with a little bit of a German accent, let's say it like that. But basically, what happens here happens in a lot of countries all over this world. So basically, the challenges are pretty much the same. At least in Germany, we decided about a decarbonization until 2038. Decarbonization is worldwide a big issue. We want to get rid of our power plants that are fired with coal, with oil, with gas to reduce the CO2. Nuclear phase out, there's a missing. That is something I would say specific for Germany, that we decided to switch off all power plants. This happened actually this year in April. Ta-da, we're still here. There was no bigger blackout so far, knock on wood. Um, More and more decentralized energy resources are connected to the networks, because if we switch off the big power plants driven fired by coal, by oil, if we switch off the atomic power plants, so what's left? There's DERs, there's water power plants, for example, and stuff like that. And these DERs, they connect on different levels in the network, which is challenging sometimes, because it's a different way of operating that grid, that in comparison to how it has been done some decades ago. And of course, we have the electric cars, we have the heat pumps. This is something we still will figure out in future. From my experience, if we talk about European countries, Norway is one of the most far in regards of, or most advanced in regards of amount of electrical cars in the network. So all these cars need to be charged somewhere, somehow. That needs electrical energy, and the grid might be not prepared for that, from coming from past times calculations about the power consumption. So the challenges for the grid operators is clearly the unknown amount of generation and consumption in the grid. There are blind spots, because coming from the old structures of atomic plant, power plant on the top of the food chain, transport level, distribution level, and the customer at the end, we need to measure what's going in that network on the top. We measure what's reaching the customer, and that's it. And then we basically can calculate what's happening in between. The moment you start to feed this different voltage levels with different DERs, with different renewable energy suppliers, this calculation does not work anymore, because you see what's coming from the big power plants, but you don't know what's going on in between. The DER might feed a customer, and you're not seeing it, because you don't have any measurement points in between. Specifically, we're talking here about the substations, where in the classic network there is no measurement and no information. That has to be that is actually a blind spot in lots of networks. We have an unknown direction of energy flow, again, coming from the old top-down structures. The modern distribution networks, we can have backwards flows depending on how strong the renewable energy is supplying the network. It might be that the transformer, which is basically thought to supply the customers, actually feeding back to the network, because the energy is not needed locally, so it's fed back to the next higher voltage level. And if the cable is not big enough, if the consumption is not high enough, we can have problems in voltage levels. So if we're feeding too much in, the voltage goes up, of course, and that is only possible and allowed for a very narrow range. The regulatory authority is adapting typically the regulations every few years, especially if we look here in Germany, but also in other countries. The outage time that is allowed without penalty is less and less by the year. So also here there's competition and challenges to reduce the power outage times. So what does that mean? That is now not challenges. This is now what has to be done, what has been done the last years, and what will have to be done within the next years. We absolutely need more measurement points in the distribution grid, clearly in the medium voltage level. We need faster fault clearance. If we want to reduce the power outage time, this is the way to go. And of course, we have to monitor and control the DERs. This is learning by doing, actually. Especially here in Germany, we started, I would say, like 10, 15 years ago with DERs. In the very beginning, they were hardwired to the networks without any control in between. And over the years, we saw there's problems. There's the influence of the frequency, which is most crucial for the stability of the network. There's the influence on the voltage level in that network. So we absolutely have to have a way to control these DERs. DERs are normally operated by somebody else than the distribution grid operator, which somehow has to deal with what's going on there. So there has to be a control mechanism that allows the distribution and the transport grid operator to reduce the amount of electrical power fed by the DERs to control the overall stability of the network. This is a big challenge, and it's done step by step, starting with the biggest DERs. They are already controllable. Now, at the moment, there is the medium-sized DERs are retrofitted with these possibilities. And at the end, most probably also the small DERs will have that function as well. That's it. That was a very quick look at how power supply grids are working. I hope you like the video. If so, please remember to follow my channel. And if you have any questions, feel free to contact me via my webpage, via email, or via YouTube, of course. Thank you for watching.